So I will start once again. So as I was telling you the story that today we'll be discussing about the use of neutron for study of condensed matter is about using neutron for structure of material. So there is some small delay. Yeah. So as was mentioned earlier also, Professor Chidambaram, thermal neutrons and cold neutrons, energy in the range of 1 to 500 millielectron volt are available in these thermal reactors. When I say, and they have an ideal and unique probe of microscopic structure and dynamics because their wavelength typically in the range of 1 angstrom. It can be 1 angstrom, 4 angstrom, 5 angstrom, but in the range of angstroms. And many length scales in condensed matter are matching with this wavelength. So this is also true for X-rays. What made Lave think that whether we can do diffraction. So it makes it ideal tool for structure or in general, if I may say, for diffraction. In addition, the energy of these neutrons are quite low. Unlike a 1 angstrom X-ray, it may have an energy of tens of kilo electron volts, but this neutron has the energy of millielectron volts. So I will like to explain this to you that neutron coming from a reactor, actually in a thermal reactor, there is something called a moderator. This moderator brings the energy of the neutron from mega electron volt down through ping pong ball collisions. So these neutrons, when they're cooling down, it thermalizes with respect to the nuclear moderator, and ultimately they have an energy distribution which is at the temperature of the moderator. So typically, this is a Maxwellian distribution with a peak around 30 millielectron volts, and in this Maxwellian, you have a portion which is typically, we say, neutron energy less than 5 millielectron volt, and that gives us handle for using them for very slow dynamics. At the same time, we also have neutrons which are called hot neutrons. They can be used to understand structure at very short length scales or reasonably high energy excitations in solids. So we use one particular energy in our spectrometer. We choose a particular energy in the spectrometer that we design. This energy is chosen from a beam of neutrons, and then it is made to impinge on a sample. So typically it looks so the source of these neutrons predominantly are reactors. So we have right now the research reactor Dhruva, which is located in Bombay, Mumbai. The best research reactor run by France, Germany, and Britain at ILL Grenoble. We are planning for a high flux research reactor, HFRR, which will come at the east coast of the country. Also, in addition, these days, there are proton accelerator based collision neutron sources. So these are accelerator based sources. So these are pulse neutron sources, and the spectroscopy is different. I will discuss it later. So we have reactors and you have accelerator based neutron sources. So this is how it looks inside Dhruva reactor hall. Now here you can see why can't I go back? Oh, sorry. So here This is the wall of the reactor. This is a cylinder of outer diameter like 20 meters. The actual reactor core is at the center of it, and neutrons, there are neutron beam lines. Neutrons come down to these instruments, go out through this guide hall, they come down through these beam lines and impinge on your sample, and then we have neutron detectors all around. Typically, this is how neutron nuclear reactor hall for research reactor Dhruva looks like. Similarly, yeah, this is the experimental neutron hall of ICIS, Rutherford Appleton Laboratory at UK. There is a spallation neutron source in which a neutron beam bombards a target like tantalum, generates lots of neutrons, not through fission, but through a reaction called spallation. And these neutrons are born with very high energy, and these neutrons are brought down in their energy using a moderator similar in a reactor, and this pulse neutron beam is sent to different experimental facilities, like you can see here. All these experimental halls, all these experimental lines are there. For example, you can see one beam line here, one beam line here, one beam line there. So they look like huge industrial facilities, but the working principles are based on pure physics and the design also, and that is what we are going to discuss in this course. So just I will get back to this later. It is just I'm trying to show you the plan of the nuclear reactor Dhruva. So this is the plan of the reactor Dhruva, in which I show you this is the core of the reactor, and we have created holes drilled through all the shieldings reaching up to the core, so that the neutrons can come out from these beam lines. They can come out from these beam lines, and our spectrometers are built outside the biological shielding. So spectrometers are built here, and for various purposes, and the purposes will be discussed. Like there will be diffraction spectrometers, there will be inelastic neutron spectrometers, there will be small angle neutron spectrometers, there will be polarized neutron reflectometers. And actually, I wanted to show you that we also have something called, very interesting thing, neutron guides that are carry neutrons out by 30-40 meters from the reactor hall. And we are allowed to build instruments. I'm sorry, my hand is wobbling. It's a straight path, the neutron. And we have a small angle neutron machine here, a polarized neutron reflectometer here, and another small angle neutron machine here. So we can build instruments inside the reactor hall and also in guide tube laboratories. And in these days, you find large guide tube laboratories where instruments are built routinely. So again, back to thermal neutrons, let me emphasize, wavelength is close to interatomic distance, as I told earlier, just as energetic as atoms and molecules in condensed matter. It's neutral, that's a very big advantage, gets deep into the sample. And that is contrast between isotopes and neighboring atoms in periodic table. This was mentioned by Dr. Chidambaram. This is a very important technique, especially later when Professor Aswal will be talking about small angle neutron scattering. He will touch upon this in more details. An important thing is that there is a magnetic spin associated with the neutron. So this is useful for magnetic materials, especially microscopic or mesoscopic magnetism. Microscopic magnetism is done by using neutron diffraction, which is similar to X-ray diffraction, for which many of you will be familiar. It's a non-destructive characterization, importantly. And of course, another interesting thing is this part. As I showed you earlier, told you earlier, that the neutron scattering cross section or scattering amplitude, it goes zigzag over the periodic table, unlike X-rays. X-rays, they follow Moseley's law. Yeah. X-rays, they follow Moseley's law and vary systematically across the periodic table. So it goes as Z minus mu Q, if I remember it correct. Unlike that, because neutron interacts with the nucleus and the interaction depends on the neutron spin and the nuclear spin, so it can vary between the two isotopes. And there are contrasts, for example, between hydrogen and deuterium, or between nickel 62 and 60 and titanium, which is negative. So we have materials with negative scattering length, we have materials with positive scattering length. Most importantly, the scattering cross section is quite strong in the lower side of the periodic table. We know that X-rays, using X-rays, you cannot see low Z materials. Actually, almost up to oxygen, you don't see anything using X-rays. Whereas neutrons are scattered by low Z material. Actually, hydrogen is a very strong scatterer of neutrons. So hydrogenous material, or sometimes selectively deuterated material, they can be used in neutron scattering, whereas these material or these atoms cannot be detected using other techniques, most importantly using the X-rays. So now I will get into the basics of neutron scattering. So in principle, it's a very simple technique. If I see, uh, if you have an incident neutron beam of certain energy falling on a sample is a conglomeration of atoms, molecules, and there is structure in it, local structure, global structure. By global structure, I mean crystallographic structure. At the same time, there are structures which are, for example, precipitate or agglomeration of a micelle. These are mesoscopic structures. So there is structure and dynamics in the sample. We have an incident energy and momentum. How we do it? So we choose from a polychromatic beam of thermal neutrons a beam. So how do we choose it? I'll just try to sort of quickly tell you. A polychromatic beam of neutrons beam of neutrons So a beam of neutron comes out from a reactor. This is polychromatic. So there are many lambdas. Usually what we do, we have a single crystal in its path. So it scatters out a particular wavelength of neutrons, which is 2d sine theta is equal to n lambda. So using a Bragg crystal, we choose one particular neutron energy and impinges on the sample. This story may be slightly different when we talk about time of flight spectroscopy, but right now I will not load you with that. So this is the scattering process. So, and once the neutron is scattered by the sample, it is detected in a neutron detector. In this scattering process, there are two things happening. One is change in momentum energy. This is important for all of us to understand that we are studying material through a scattering process. So we will be, all our experiments, whatever I am going to talk about, is in q omega space. Momentum transfer is h cross q, and and the energy transfer is h cross omega. So basically, we are trying to map our sample in q omega space, and I'll get back to it later. And from here, we'll try to get ideas about the structure and dynamics in the material, which is right now I may say it's the Fourier space of this q omega space. And what we see actually, either we see d sigma by d omega, that is neutrons per unit solid angle without bothering about energy, or we see d2 sigma d omega d, which is neutrons per unit solid angle per unit energy interval. So that means I will be measuring the energy of the outgoing neutron, and that will be for dynamics of the material. Here that for an elastic experiment, by elastic I don't mean elastic classical sense. By elastic we mean elastic as when there is no energy transfer between the neutron and the sample. In that, if you don't consider that energy transfer, then for an elastic experiment, for an angle theta, this is 2 theta. If I consider that the wave vector transfer is given by q is equal to 4 pi by lambda sine theta. Now I have put a question mark here because I'll leave it to you for a crystallographic, for a crystal, for an arranged atomic system, what this q should be, we all know. I'll come to it later. So let me try to derive a general expression neutron scattering cross section. So it is elastic, so I am not talking about any dynamics in the system. If n is the number of, is the flux of neutrons incident on the sample, and neutron scattered inside a solid angle, so basically this is a simple geometrical constructions where neutron comes in this direction, there is a target, and I have written down the polar coordinates as r theta phi. It goes inside of a detector here, which is making an angle theta with respect to the z-axis and phi with respect to the in the horizontal plane. All of you know this will be this expression where the solid angle is given by sine theta d theta d omega. It's fairly simple to understand. So now I'll use an expression which is known as Fermi golden rule. I will go slow here and explain term by term, but I think those of you who are the masters in physics, they will be very much familiar with this expression. And those who have not done masters in physics or unfamiliar, I will tell you that this is nothing but a transition probability. So here, under is a quantum mechanical expression for a system which is initially having a wave vector psi k. When the momentum vector is k, it undergoes a change in scattering and goes to psi k prime under the influence of this potential. This is what the sample provides, the potential, the scattering potential. With this is the transition probability given by Fermi golden rule. It is basically an integral in which you so basically it is related to this is the transition probability from a state k given by this integral, apart from a few constant terms which you have written. You may, for the time being, you may just accept them. So this is the transition probability which is given by d3r. This is a three-dimensional integral. D3r, basically this r is a vector, and there is a density of states for the final state. That means if it is a free neutron, then this is nothing but d3k de, number of unit k in a volume element d. So this is the transition probability given by a small volume in k space that gives you the transition probability. And as I told you earlier, that this incident wave function is a plane wave function. We create it that way. We make a neutron beam, a parallel neutron beam, so I can represent it by a incident wave vector. Rho k prime e is given as, this is basically, if I may write it, I'll go very slow here and understand this thing. So one is the psi for a plane wave. This is because this is when I consider my sample to be a box of side L. So this is a normalization term. This is a plane wave function. And as I wrote earlier, the transition probability is given by Sorry, I will write about again. Now this rho K prime E is given by this term comes because for box of side L, you have one K value in 2 pi by L. So density is L by 2 pi, and because there's X, Y, Z directions, so it is L by 2 pi Q. And then comes the term D3K DE. Now this is the D3K is the elemental volume in K space, which is given by K square phase space dk d omega. This is D3K. And when and here also I use the thing that dk by de I will obtain from for a free neutron E is equal to h square k square by 2a. So if you plug in all these things in it, then I get rho k prime E equal to m k by h cross square L by 2 pi q and d omega. This is what I want to show you. So now I'll get my transparency. Yeah. So ultimately we try to evaluate this expression, and over here I must mention you before I go any further that often this integral I'll be denoting with similar integrals like Dirac's bracket notation, where k prime vk is basically d3r. I mean, this is a three-dimensional integral psi star k prime vr psi k. This integral is given for us. For physics people, it is quite common, and for most of you, it's a repetition. But for some of you, if it is new, accept it, and we'll go ahead. So once I get this rho k prime, what I get actually, and the flux of neutrons is nothing but velocity by L cube, volume of the thing. So H cross K by ML cube, psi I have given. So ultimately, I get an expression for d sigma. So this is, I am calculating for a system where I have not considered the dynamics. To start with, I have got a static system in which I am trying to evaluate the neutrons scattering per unit cellular angle for a neutron of incident energy and wave vector k, and this is the expression I get finally. I'll be uploading this talk in the site, so you can download and have a look at it. Any queries, you please write back to me. So actually I get an expression which is fairly simple, which is d sigma d omega. That means this is the neutron scattering cross section per unit solid angle is given by this expression m by 2 pi h cross square and then this bracket notation. Basically, this is the fun of quantum mechanics, that you calculate the amplitude and then you square it, you get the probability. So we always calculate probability amplitude and square them to get the probability. And when I use this as kk prime, then I can write d sigma by d omega equal to f kk prime square. Here I would like to mention one more thing to you, and that is when I say k psi k prime psi k, that means this will be looking, if I break them up, it will look like k psi k prime psi k. So I can move around these things and sort of find out the square. So this is how we work with this square. So please remember this, that this is a square in which you have to actually two integrals are multiplied and each integral looks like this. One is the complement of this, because one will be the, you have to take a complement of this thing. That's how it, that k prime psi k becomes k psi k prime, and the other is integral itself. So it is like a complement of a, complex conjugate of a multiplied by a. So if you remember this, all our future tasks will be pretty simple. So we have derived the scattering cross section d sigma d omega, which is a square of an amplitude, basically f star kk prime f, that will give us the scattering amplitude. But so far it has been only some bit of jargoning and mathematics. What do we get from here? Now I will define the neutron nucleus interaction potential. Now, in case of thermal neutrons, the neutron wavelength, the de Broglie wavelength, is of the order of angstrom. Few angstrom, fraction of an angstrom, but of the order of angstrom. And the nucleus, the size is femtometer. It's around 10 to the minus 5 angstrom. So Fermi saw this and he introduced something known as Fermi pseudopotential. So basically, for the neutron impinging on your sample, the potential is a delta function potential. It's a delta function potential, and then we represent it by a delta r minus r if nucleus is sitting at r, then this is the delta function potential. This is known as Fermi pseudopotential because this is an approximation and recognition of the fact that the neutron interacts through strong interaction with the nucleus, and the nuclear dimension is much smaller than the wavelength, the de Broglie wavelength of the neutron. Now, when if I put it as here as delta 0, if I take only one nucleus which is sitting at the origin and put it in expression for the expression for d sigma d omega, which is this expression, I put a delta 0 here, then what I get is this d sigma by, and of course I have put a constant term 2 pi h square by m simply to get rid of the m by 2 pi h square. I get d sigma by d omega as b square, or sigma is equal to 4 pi b square. Now it is tangible. So basically, this scattering gives me the scattering cross section, quantum mechanical scattering cross section which is given by 4 pi b square. Classically speaking, if I put a disk of b radius in the path of an impinging beam, it will provide a scattering cross section which is equal to the area of the beam, pi b square. Quantum mechanics only adds a 4 to it. So for a single scatterer, it will be 4 pi b square. And that's what the scattering length is all about. So using, let me again mention it to you. So I started Fermi golden rule for a scattering process in which without any energy exchange, the neutron goes from k to k prime. The expression is this. Then a little bit of where I put the VR as a delta function potential, as I explained sometimes back, because the nuclear dimensions is much smaller than the neutron wavelength, and the density of states I calculated using d3k by dE, which is the density of states for a free neutron at an energy E at a wave vector k prime, and just plugged in a few things, and I get for a single scatterer a scattering cross section of 4 pi b square correctly. So for systems that we will be studying, this b is an important factor, and this is what for a single scatterer. The next problem I would like to deal with for a rigid lattice. For a rigid lattice, this same expression, now I have the scatterers sitting in a lattice. So there are atoms or nuclei, they are sitting in a lattice. It's an arrangement of lattice structure where one of them possibly, this is the, sorry. So for a arrangement of atoms, one particular lattice point, if I call it L, then I can consider the lattice as a summation of delta functions sitting rigidly, and each side has got a scattering length of BL. That means if I took it out and consider an individual atom, it would have given me 4 pi b square. Now, these atoms are sitting rigidly at sides L, but this part I'll be tackling in the next lecture. Today I have just given you the first part of the formalism for a single lattice point, and next lecture will be, I'll be dealing what I get for a rigid lattice for a neutron of wavelength k.